equal and opposite results. So you're gonna, instead of AD, you're gonna get minus AD. So the gain is gonna be JMRC over 2. All right. So that's the computation of AD. Let me repeat something here, very important. Why did we have to do that? Why did we have to write equations like this? Because I wanted to simplify the problem mathematically and mimic the mathematical representation by 2 circuits. So I am simplifying the original circuit, which is this circuit, by having 2 simpler circuits to deal with the situation. One of these circuits is going to determine AD, and the other circuit is going to determine a common mode. Where is the simplification coming from? The simplification here is coming from the fact that we utilize symmetry. So we have a symmetrical situation here. The right-hand side, and there is a mirror image here for this circuit. So when you have a mirror image situation, it is sufficient to analyze only 1/2 of the problem. So it cuts down the effort by 50%. That's the whole idea. So it's true that I splitted the original circuit into 2 circuits, but each one of these resulting 2 circuits, we cut down the analysis time and effort by 50%. But the solution is meaningful now. We can attribute an outcome to differential gain and attribute the other outcome to the common mode gain with ease. Now let's determine AC. All right, for AC, we're talking about the common mode. How do we calculate the common mode component here, AC? Let's remove the differential component. How do you remove the differential component? By taking that VC here and VC here. You see? That circuit. You're taking VC here and VC here. So you have 2 equal inputs. When you have 2 equal inputs, the differential component is 0, because the differential component by definition is the difference of potential between the 2 inputs. When you make the 2 inputs equal, the differential component is going to go to 0. So the circuit boils down to this. So there is a symmetrical situation. Now we can simplify this. We can solve this. How? And instead of saying you have a single RE here, you can say that you have twice as much as 2 resistors. Each one of them is 2 RE. So 2 RE in parallel with 2 RE is going to give us a single RE. And then we can do the bisection. Why do we do the bisection? Because the circuit is symmetrical. And by definition, ABC electronics say there is no current between 2 equipotential points. So these 2 points are equipotential. Due to the symmetry of the situation, there should be no current here. So I'm making a cross, red cross here. So you're removing that.
Professor.
Raise your voice, please.
Hello? Can you
Yes.
hear? Would it matter which side we solve for first? Or it doesn't matter?
Does it matter which what?
Which part we solve for first, the left or the right-hand side?
For this circuit, you mean?
Yes.
We are not making any preference now.
Okay.
We are, no, no, I see what you mean. It doesn't make a difference if you consider this input and this is your output, or this is your input and this is your output. That's probably your question.
Yes, thank you.
It doesn't make a difference.
Yes, I didn't think so, but I wanted to confirm.
Yeah. Due to symmetry, you can the whole idea here is that we want to get rid of 50% of the circuit. We want to get rid of half of the circuit and play only with the other half. Thanks for your question, because at least I know that there are people who are awake in the lecture. It gives me the feeling that there is some kind of ideally the lecture should be a discussion between the professor and the students. I shouldn't be talking all the time and you listening all the time. That's not a good sign. You should participate by asking questions.
Thank you, Professor.
You're welcome. So now we're gonna remove that part. So we will end up with something like this. When we remove this part, we just remove it on paper, but we don't remove anything in the lab. You go to the lab, don't do anything, don't do anything here. We're talking here, that's like a modeling situation. Many things happen in the lab which make me laugh, I'll tell you about those later. But you shouldn't make any wrong assumptions in the lab. So we're gonna work only with half of this, which half, back to your question, it doesn't matter. Any half is good. Let's say we're going to be working with this half, with the left half. So the gain of this, you have the knowledge from 330 to find the gain, the minus GMRC over 1 plus 2 GMRE. So now you have a formula for the common mode gain. We have a formula for the differential gain. What's left? You need a formula for the common mode rejection ratio, which is 20 log the absolute value of the quotient. Yeah, so that's the common mode rejection ratio. 20 log 1 plus 2 GMRE over 2. So far, we have been discussing the single output scenario, single-ended output scenario with a ground. Let us suppose we want to discuss the situation when we take the output differentially between these 2 points, between V output 1 and V output 2. What's the difference between V output 1 and V output 2? The common mode rejection ratio is going to be infinity. The common mode rejection ratio is going to be infinity. Why is that? Because when you do that, there is no common mode component. You see what I mean? When the 2 outputs are equal, where is that? Let me go back to that point. differential input, differential output case. Common mode rejection ratio is infinity because if you have a situation when you have equal outputs, when the two outputs are equal and opposite, what does it mean? That the common mode part is 0. Suppose you have a plus 1 volt here and minus 1 volt here. Well, there is a differential component at the output of 2 volts, but there is there is a 0 common mode output. See, 0 common mode output. So you're dividing in the numerator the differential part divided by the common mode part. You're gonna get infinity. So let me say this. When you take the output differentially between VO1 and VO2, you're gonna get 0. You're gonna get infinite common mode rejection ratio if you take the output differentially between these 2 points. You're gonna get infinite common mode rejection ratio.
Professor, are we over the class time?
Yeah, I'm done already. Yeah.
Oh, perfect.
Yeah, I thought to finish that little part before we go. By the way, let me ask this: do you have classes right after this?
Yes.
Yes.
When does it start?
Like in
1:30.
5 minutes.
5 minutes?
Yeah.
Okay, I owe you 5 minutes. Okay.
Don't worry about it.
Okay, take care.
Have a good day, Professor.
Stay tuned. I'll be sending you some homework. Yeah.